Hello, everyone. In this section, we are going to I'm going to show you one of the applications of the Venn diagram. As we saw before, the Venn diagram is a visual representation of sets. You draw a rectangle to denote the universal set, and inside that rectangle, you draw your circles. For each set is represented by a circle. So you may have disjoint sets and we have overlapping sets and so forth. But if you noticed in the last presentation, to do an intersection or the union or any operation on sets might not, you can ignore about the Venn diagrams really. I mean, you can do this directly, but sometimes the Venn diagram is really a very practical way to solve things very easily, as we are going to see in this application. So this is a classic application in every set discussion, in every textbook, you find those applications. So here's what we're going to learn. We're going to use, again, the Venn diagram to solve application problems. So let's take a look at this application. It says at Erie Community College, in the college, a survey was taken to determine whether or where students studied on campus. So they talked to 250 students, and these are the results that they gathered from surveying these 250 students. They found out that 167 students studied in the library. 138 of those studied in the cafeteria, and 75 studied in both the library and the cafeteria. So we need to be careful here. When I say 167 study in the library, it does not mean they study in the library only. Actually, 167 study in the library, and among those 167, we have 75 studied in the library and the cafeteria. So this 167 is including those 75. Because as you can see, it didn't say, or it doesn't say, they studied in the library only. No, if I say, well, I go to Starbucks, it does not mean I am implying I don't go to, I don't know, Panera Bread, for instance. So when I say I go to Starbucks, it doesn't mean anything about where else I go or I don't go. So that's one of the tricky things in these type of problems, just like I said also. So here 138 studied in the cafeteria. Well, among those 138 who studied in the cafeteria, we have 75 who studied both in the library and the cafeteria, because those 75 studied both in the library and the cafeteria, they should be included in these two categories, because 75 also studied in the library, those 75 also studied in the cafeteria. And then here are the questions. For example, just given this one here, can you tell me how many people, for those who say that, how many people studied in the library but not in the cafeteria? How many people, for example, didn't study in either the library or the cafeteria? They studied somewhere else. So based on this, so why can't you just pause this and try it and see if you are going to be able to answer these questions, right? So, okay, so I'll assume that you paused it and then you're playing it now. So here's how are we going to do it. Suppose that we are going to have all these people being the elements of the universal set, because we surveyed 250 students. So everybody here is included. So those are the 250 students that we surveyed. So we are going to assume that the universal set is the set of all these 250 individuals. We don't care about their names, we don't care about their majors. When you read the word problem, there's nothing that suggests that we need to find out their names or where they live or anything. We are just concerned, or we are looking for the number of people, let's say, who studied in the cafeteria, not the library, and vice versa, or how many people studied outside of these two locations. So the cardinality, or the cardinal number of the universal set, is 250. Now, the cardinality of people who study in the library is 167, because it says that verbatim, it says there are 167 people studying in the library. So here we have so far the universal set that contains everybody. Now we create a new set. We can call this L for library. I mean, we could have called A and B and C or anything, but L is more meaningful because library L. So we're going to have a set within this universal set called L that has 167 students. And we are going to have a set called C for cafeteria. And the cardinality of C is 138 students. And of course, this is a very important thing. So how many people study in both? When I say in both, means and, remember, and can be translated into intersection of two sets. So the cardinality of L intersect C is 75. So now when we create the Venn diagram, we are going to have this 75 here. So this here is L, the set, the blue one is the set of people studying in the library, and the red one is the set of people studying in the cafeteria. While 75 is justified already. Why 75? Because this region is the intersection region. So we have 75, region 2, 75 of people study in both the library and the cafeteria. Well, how did they come out with this 92? Well, if you look how many people study in the library, we have 167. If you take 167, from that you subtract 75, you find 92. And you do the same thing, we have 138 students, right, who studied in the cafeteria. You subtract 75 from that, you get 63. So these 63 are the people who study in the cafeteria only. These 92 are the people who studied in the library only. And the 75, well, those people, they go sometimes to the library, sometimes to the cafeteria. But if you add up all these three numbers, 92, 75, 63, it's not 250. So the difference between, if you add all these numbers and subtract that from 250, you find 20. That's why we put 20 here. If you see the number 20 is outside of all these sets, means that 20 people among those 150 students, these 20 people, they go somewhere else to study, where we don't care, but they don't go to the library, they don't go to the cafeteria, all right, they go somewhere else. So again, region 2 is the intersection, is 75. Region 1 is the number of people studying library 167 minus 75, that gets you 92. And the third region, people who study in the cafeteria only, which we have 138 minus 75 equals 63. As you can see with the Venn diagram, makes life so much easier. If you have attempted this exercise without the Venn diagram, it's going to be a little bit tricky. I hope that you paused it before so you can see the difference. Well, this is the trick, really. I mean, we could have added another place, for example, I don't know, a classroom or something, or home. We could have extended this exercise to when we surveyed 250 students. We are concerned with 3 locations: the library, the cafeteria, and home, people who study at home. And we could have a third set. Actually, there is an application right after this example that tackles 3 sets, and I will let you do that. So if we add 1, 2, and 3, like I said, we get 230. So, well, this is not the number of people. If we get more than 250, it means we have done something wrong. So 230 from, if you subtract that from 250, we get 20. So 20 people are the ones who studied outside of these 2 locations. After you set up the Venn diagram, everything else is easy. So if they ask you how many people study in the library, not the cafeteria, in the library, not in the cafeteria, well, it's 92 plus 20. Well, it's just 92, I'm sorry. How many people who study in both of them? Well, 75. How many people didn't study in any of those places? Well, 20, and so forth. Now we can answer these questions. So again, 20 students didn't study in the library or the cafeteria. 92 studied in the library only, not in the cafeteria. 63 studied in the cafeteria, not in the library. I think you get the point here. And these are the answer to our questions. Now, if you look at another set, we can extend this to 3 sets, 4 sets, or even more. But of course, more sets is going to be more trickier. Here is another example. It says Liberty Travel surveyed 125 potential customers. The following information was obtained. 68 people wish to travel to Hawaii. 53, they wish to travel to Las Vegas. 47 wish to travel to Disney World, and 34 to Hawaii and Las Vegas. 26 wish to travel to Las Vegas and Disney World. 23 to Hawaii and Disney World, and 18 people, they wish to travel to all the destinations. But we need to be careful again. Those, you see those 68 who travel to Hawaii, Well, 18 of them also, 18 of them would like to go to the other two destinations. So what we're going to do here, we're going to have the 3 locations, right? So you can see 18, you see this region here, 18? Let me use my, so this region here, 18, so this region here, 18, this is the region that is belonging to all the sets. We have 3 sets, right? So 18 wish to travel to all of them. And this number here, 22, of course, I'm going to show you how we get the 22. These people, they don't wish to travel to Hawaii or Disney or Las Vegas. Well, maybe they want to go somewhere else, but we should not care about that. So all the visitors or the visitors that want to go to all the regions is 18. Now, how many people they want to go to? If I let's say here, let me highlight this region here. If I highlight this region, Hawaii and Disney. If I highlight this region here, this one here, this is among the people who wants to go to Hawaii and Disney. If you look at the problem before, they said we have 23 people. Let me go back. So he said 23 people, they want to go to Hawaii and to Disney. Now, I have already listed 18 of them, right? I already listed 18 of them. So 23 minus 18 is 5. So what is 5? 5 is the people they want to go to Hawaii and Disney, but not Las Vegas. I think you get the trick, and you do the same thing. If I cover this region here, what is this region here? This is the overlapping between Las Vegas and Disney. So how do you get the 8 here? We went back to the exercise and saw the difference between 18 and that number is 8. Which is 26. They said 26 people, they want to go to Las Vegas and Disney. But since I already listed 18 of them, means that 8 people, they want to go to Disney and Las Vegas only. Well, you see, just like the first exercise. The first exercise, we had 2 sets. And the library, those who want to study in the library and the cafeteria. Now we have 3 sets, and you can even make it 4 sets. It's just with 4 sets and more, it's going to be a little bit challenging to have a good diagram. So you need to really have a good, enough space to draw these 4 sets and make sure that you have them all overlapping. And the region that belongs to all of these 4 sets is the region of the intersection of all these 4 sets, and you go from there. Like these problems, you always start from inside, outside. You want to start with the common between the 3 sets, and you start subtracting and you work your way out. Once you get those numbers filled, you add them all together and you subtract that from how many people were surveyed, and that's how we get 22. So Hawaii and Vegas, Disney and Vegas, Hawaii only. If you want to do Hawaii only, well, if you go back to the exercise, they told you that there are 68 of them, they want to go to Hawaii. But how many don't want to go to Hawaii only? Well, you take 68, you subtract 5, they subtract 18, subtract 16, get 29. 29 people, they want to go to Hawaii and nothing but Hawaii. Well, when I say nothing but Hawaii, they may want to go to Morocco, or want to go to, I don't know, Spain, but we are not talking about that. We are considering only Hawaii, Disney, and Las Vegas. These 29, they don't want to go to Disney and they don't want to go to Las Vegas. They want to go just to Hawaii, because you can imagine that this survey is giving them these 3 places and to pick these 3 places only. So that's how it goes. And we do, it's very repetitive, and you do region 3, region 6, 7, and so forth. And at the end, you subtract the total 125. You take 103 when you add up all these numbers, subtract 125, that gets you 22. And then once you fill all the regions, then you go to the exercise and start answering your questions. So as you can see, 22, like one of the questions says, well, how many people, they don't want to go to any of these places? Well, the answer is 22. Yeah. 29 wish to travel to Hawaii only. For example, 16, they want to go to Disney only. 11, they want to go to Las Vegas only. 18, they want to go to all of them. If you look at 16, if you look at those 16 people, they want to go to Hawaii and Las Vegas, but not Disney. I think you get the point, right? Yeah, so this is pretty much the trick of this one here. You start from the intersection and you start working from the inside to the outside. Well, this is one of the applications of Venn diagrams. This marks the end of our discussion on sets. Sets can be, a lot more than this. You can actually have your degree in sets, and if you degree in mathematics, it's still a lot. But I hope that this gives you an idea about how to work with sets from a mathematical point of view and how sets are applied in real life, just like this example we covered today. Okay, well, now I think you can go and finish your homework and start doing the test if you want to. If you have any questions, let me know.